All right, let's get started. So what we're going to talk about today is a very important chapter in this course. It's convolutional neural network. So this is a special type of neural network that is pretty different from the regular neural network that we covered so far. So in the previous 2 weeks, we started from shallow neural networks and then the deep neural networks. And in those what we call regular neural networks is the so-called feed-forward ones, which means there are layers of neurons, and between layers, all the neurons are fully connected. So each one of the neurons in the current layer is fully connected to all the previous neurons, from the previous layers. And sometimes we call it a fully connected or feed-forward neural network. Okay, but today the convolutional neural network, or ConvNet or CNN, is a you will see it's a special type of network that has different architecture, and also it is important because it brings significant boosts in terms of the performance of modeling images, of increase the performance like accuracy in image classification tasks or objects detection tasks. So primarily in computer vision studies, in computer vision, in the field of computer visions. Okay, but also recently we find that the CNN or ConvNet has a much broader application than just in computer vision. It also has some applications when handling sequential data, like language data, natural language understanding, and so on. Okay, so that said, this is a very important contents of this course, and we will start from the basics. Okay, so we're going to look at what the term convolution means. So what kind of a mathematical operation it is. That's something we will look at first. And then we will introduce a bunch of terms that are involved in the convolutional operation, which is padding, stride, and convolution over volume, and pooling. Okay, so finally we're gonna put together all the little piece of tools, techniques, like convolution with padding, convolution with strides, and pooling layers, so that we can have our very first simple convolutional neural network built up. Okay, so that is the basic outline of this first chapter for ConvNet. Okay, let's enter this slide. So it's a special type of network, okay? And it has a broad range of applications, like in basically any CV-related application scenarios that you can name, okay? And also, as I said, it's extended to other fields like speech recognition, text classification, and so on. Okay, so in this demo, this picture here, the results of detecting objects in the image or in the video clips is basically a result of applying the algorithm, the object detection algorithm that is designed based on top of ConvNets. Okay, so it is able to quickly locate the positions of different objects, and also it gives the probability of the label, of the object label that the network detects. Like the bus is labeled with a bus label with 98% as probability. Okay, and ConvNet also, in this specific example, like neural artistic style transfer, it is able to like transfer, first of all, learn the styles as some hidden layer, as some hidden representation from some existing art piece or artwork, and then apply that layer, apply that style to a like modern picture or a different piece of art, so that it creates a mixture effects of the layers. It looks more like a filter. So are you, well, it does, the the network does come with something called a filter, right? It's like creating a filter effect upon a picture. But that filter is not a fixed one. It's not a predefined filter. Actually, I appreciate that you mentioning the term filter, because so typically when we talk about the future, it's something like a something that's already defined and we can immediately use to be applied to a picture and then create some effect that we want. And that is okay. So after a convnet is trained and after all the parameters are fixed, then it can be used as kind of a static filter like this. But what's more interesting is the training process of the parameters. So given a filter, that's whose parameters are not fixed, whose parameters can actually be tuned or be learned during the training process, then that filter will do much more than what a static filter can do actually. Okay, so that's another application. So I think in the later chapters of this course, we're gonna talk about the generative network or generative models. So it's getting very popular recently that we built generative adversarial network, which is also called GANs, and that is able to let the network to generates data points. Like it generates a picture of human faces or generates the artwork from totally random inputs. So that network is powerful in learning the existing high-level features or high-level patterns in the training sets, and be creative in generating totally new data points. Like it can generate a human face that never exists before. Like it can generate a cat, like a dog that never exists in the training data sets. Okay, it's like creating something totally new, and that's like GAN's model also utilizes the convolutional neural network architecture that we're gonna introduce today. Okay. All right. So before we started talking about the convolutional operation, we will look at why we need a different type of network other than regular neural networks. Okay. So for instance, we want to classify pictures, classify image data. Okay. And assume we have very small image data as input, which is 64 by 64 pixels. Okay, but although it's a small image, it's a pretty blur image, and it's still a lot of pixels. And the usual way, if we use regular neural network, is that we take all the pixels out. So 64 times 64 is 4096 pixels. And we just take the pixels out and put them into a very long, thin vector. and use that as the feature to represent the image, then it will result in a something by 4096 weight matrix. I put the question mark here because we don't know what the hidden layer, how many units we will have in the hidden layer, but that doesn't matter. And regardless of the hidden layer size, the number of columns is unknown because we have that many pixels in the data. Okay, so well, I just realized that maybe according to yes, I think it's correct because we put the data points, we put the data as a column vector. So the weight matrix should have the same number of columns. Yes, no problem. That's correct. So yeah, so we have a very, very long weight matrix because it has to have the column that matches the inputs. Okay, so what if we want to handle some larger image, say this beautiful image with 10,000, 1,000 by 1,000 by 3, because it is a color image. Then it has 3 channels, the red, green, and blue channels, RGB channels. So that will result in 3 million points in one vector, and then which requires a 3 million column matrix, weight matrix. So that is a huge cost. That is so many parameters to learn, and it's almost always immediately leads to the overfitting problem. Okay, we in a manually labeled image data sets, it's hard to reach millions of data points. Okay, so we are facing a very serious problem here if we use regular neural network. Okay, so that's basically why we need a convolutional operation instead of to replace the regular neural network. Okay, so when we talk about convolution operation, I think we will start by looking at a one-dimensional example. Suppose that we have a signal or a input data that is a 1D array, okay, or 1D vector, okay. So this is our inputs, and we call it a signal, indicated by the S. And also we have something much shorter, okay. We have 3 elements vector, and we call it a filter or a kernel, okay. So the convolutional operation on in this 1D space is defined by the mathematical formula like this. So we use the star here to indicate this is a convolutional operation between 2 vectors, S and F. And S is the input signal, and F is the filter. Okay, so the result of our convolutional operation is also a vector. Okay, we call it H vector, and the ith element in H is determined by basically this formula. But it's okay if we don't look at the details at the formula, and we'll just use a animated demo to show what this operation does. Okay, so what basically this operation does is to first align the 2 vectors. We put the signals above and the filters below it, and the left end of these 2 vectors, they are aligned. Okay, that is our first step, right? And the numbers in the grid is the values for each element in the vector. Okay, so the first element in the output, we call it H1. Then H1 is computed by summing up three products. And these three products is the results of applying the element-wise multiplication between the filter and the corresponding segment in the signal. Okay, so it's a summation of products. So it's basically a dot product, right? The elements in the three elements in the filter is basically identical, 1/3 for each element. And the elements in the first segment in the input is 10, 50, and 6. Okay, so that's how we get the first element in the output, which is 40. Okay, that is the first step. And what's the remaining steps is more or less the same thing, but we should move the filter one grid to the right. Like a sliding window, we slide the filter window to one grid towards the right. Okay, so that's now in the second segments within the signal, we have basically different elements, right? Although the result is the same because the new elements here is still 10, right? That doesn't matter. And we just need to compute this dot product between the corresponding segments in the signal and the filter vector. Okay, so that's the second step. And the third step, we need to move one more grid to the right. Okay, so this time we got some new values, 60, 10, and 20. The dot product between these segments with the filter results in 30. And then one more step to the right, we got something new, which is 20. And lastly, when the right end of the filter reaches the right end of the signal, okay, so that is our final step. And we will have H5 in this case. Alrighty, then we have basically 5 outputs, 5 elements in the output vector, right? So I've got a question here. So the filter value determines how many data points we sum per iteration. Yes, so in this case, the size of the filter is 3. It has 3 elements. So each time we take 3 elements from the signal. If the filter is like 2, which is uncommon, or 5, then we need to take the corresponding number of elements and do the dot product. Yeah.
Can I ask, to clarify, is the convolution operator the S times F times I, that whole thing?
Mm-hmm.
Okay, thank
you. You mean this here? You mean the dot here, right?
I guess so, yeah. Is the convolution, just for my notes, is the convolution operator like that whole function, H of I, or just like the S times F specifically?
So this is not S times I. This is the notation for convolutional operation. It denotes the convolutional operation.
I see. So that asterisk is the convolution.
Yeah, this is the, yeah.
Oh, thank you. Okay, I missed that. Thank you.
Yeah. Okay. So when we have 5 outputs, we will collect those outputs and put it into a vector, 40, 40, 30, 20, 25. And this is the results of the convolution operation upon a 1D input signal and a 1D filter. Okay. And we can do the calculation about the length, right? The output length is 5 elements, and basically 5 is the results of 7 minus 3 plus 1. 7 is the length of the input, 3 is the length of the future. So this relationship is something we will be used again in the 2D case. All right. Okay, a simple demo for 1D convolutional operation. So in the 2D case, we apply the same thought, same technique, basically. So the star here indicates convolutional operation. Okay, so this is not a multiply, this is a convolutional operation. And in the 2D space, our filter is also a 2D filter, okay? Because the input is a image, is a 6-row, 6-column, 6x6 image data. So the filter this time is a 3x3 filter, okay? And the value in each element of the filter is 1/9. So we call it an identical filter because it has same values in each element. So we'll look at the results. First, look at the shape. It said coming to the filter, would example of the artistic style be the filter? Yeah, it's I would agree with that. How do you determine what the filter is? So let's cover the rest of the 2D filters, 2D convolutional filters. Then you would have a better idea of what kind of a filter that's I'm talking about here in 2D convolutional operation. Okay, so basically in the slide shown here, a filter, 3x3 filter is basically a matrix. It's a 3x3 matrix. Okay, so and it has fixed values. Each element in the matrix is 1/9. So what if we want to apply a convolutional operation using this 3x3 filter on top of the 6x6 image? So we also need to first align the two data structure, align the two matrices. Okay, so the results, the output would be a 4x4 matrix. Okay, and if we look at the first elements in the 4x4 output, it's the first row and first column. Okay, so how do we get the first elements in the output? We basically need to take the first 3x3 segments or parts of the original image, okay, and apply a dot product between these part of the data in highlighted by the green color with the filter. Okay, so let me clean up a bit. So the 6 will be multiplied with the 1/9 here. And the 0 will be multiplied with the 1/9 here. Okay, and the 0 will be multiplied with the 1/9 here. So that is a 1-to-1 mapping relationship between the filter and this green area. Okay, and we summing up all the 9 products between the filter and the green area, we will have one value for this output cell, for this output element. Okay, which is in this case it's 4. Okay, yeah, that's true. The 6 minus 3 plus 1 holds basically for 2D operations. And the complexity, some complexity we will introduce is that in this case, we can move for more than one step each time we move the sliding window. then for example, if we move like 2 steps to the right or to the bottom, then the resulting output would be smaller because we move the filter faster. So that's something we call stride, which we will talk about in the later slides. Okay, so that's the first element. So for the second one, to the right, we basically need to move the filter 1 grid or 1 pixel to the right. Okay, and we apply the same element-wise multiplication and sum up all the products, which will give the value for the second element, for the second output element. All right, and the third, fourth. Okay, so we are done with the first row. So next, we're gonna do the same thing for the rest of the elements. So I wanna mention particularly for the second row, the starting position for the second row should be here, this 3 by 3 area will be mapped to the 3 by 3 filter. Okay, so that is how we compute these elements. And then we will move 1 step to the right. Okay, and we'll get this one. Okay, so that is basically how we do the 2D convolutional operation with some input image with a filter, then we get some output. Okay, all right. Looks pretty easy, huh? So so basically, we will apply these convolutional operations to image data with the goal to reach some effects, special effects on the image. Okay, so now we are going to the realm of basically traditional computer vision techniques. So I say it's a traditional technique because the filters so far, they are preset, they have preset values. Like in this average filter, we call it average because all the values are identified and they are identical and they are normalized by the total value, which is total summation, which is 9, right? So if we apply this averaging filter onto the original image, right? Say we have this eye, and then it will create some blurring effect. So basically, it averages all the pixels within that 3 by 3 region. Okay, so which basically makes the whole image, makes the details not that differentiable. Okay, so that is the special effects from the averaging filter. Okay, so of course we can use different preset values. For instance, this one is called identity filter. So there's only 1 in the middle and all zeros. Okay, so it's basically copied the region, the 4 by 4 region in the original image directly to the outputs. It doesn't change anything, right? It only leaves all the remaining frames, like these most outside pixels, to they basically cut those framing pixels. So it's almost a direct copy from the original one to the output one. Okay. And let's quickly look at some more features. So this one, if we put the 1 to the grid to the left of the center, it will create some shift left effects. Okay, by only keeping the left parts of the original image. So lastly, this example is quite interesting So if the filter looks like this, there's a column of ones and the column of negative ones on the right, then what this filter will achieve is to identify the vertical edge. Okay, for example, in the output for the first element is the result of applying this filter to the top left region, which will result in 0 because we have 20 minus 20, right? 20 minus 20, 20 minus 20. So the result will be 0. And the cell to the right, okay, so this time we will have some different values. We will have 60 because we have positive results. And one more to the right, it's also 60. Okay, and one more to the right, we've got 0. So as a result, applying this vertical edge detector or this special type of filter to the image, we will have something like this. So if the larger numbers in the image represents the brighter colors, then this resulting positive numbers actually indicates the edges, right? They actually indicate the edges between the left half and the right half. So I guess this is something you will learn in the computer vision class, right? So and the horizontal edge as well. Okay, so what's in common between the so many filters that we talk about is that they all had preset values. So they are basically kind of handcrafted or hand-coded filters. Okay, so this is the traditional way of image processing or extracting features from the image data. So, for example, given the inputs, sign language image like this, then we can probably apply a bunch of filters to detect the vertical edges, right? And horizontal filter to detect the horizontal edges, or different, more cleverly defined filters to detect the both edges at once. Okay, and then we will use these filters. We'll use the resulting edges or the edges in the image from the image as the basis for further object detection or object classification. Okay, so this is the thoughts from the more traditional CV studies. Like we use carefully designed hand-coded filters. Okay, but we will soon realize that all these filters, they have very significant limits, because once the pixels in the image changes, for example, if it's not a black or white image, what if the target object is different? Then we probably need to select, or we need to tune the filters slightly, because the resulting task is different. The resulting data the underlying data is different. So how do we make the filters more smart? Okay, so that is the key of the convolutional neural network. Okay, and the idea is simple. We do not use predefined filters, but we let the filters have parameters, and those parameters can be learned from data. Say we have a 3x3 filter, and each element in that filter is a parameter. we have W1, W2, W3 until W9. And if we apply a convolutional operation between this filter and the image, okay, then we are able to get some outputs. Okay, so it could be a shrinked, a little smaller image, or we could apply apply the filters for multiple times. Okay, anyway, we will get some outputs from the convolutional operation. And then, because if it's a supervised learning task, then we can compare the outputs with some ground truths. Okay, say if there is an edge in it or not, or if this is a hand image, or if which number that this hand indicates, right? We always have ground truth label. So by comparing the outputs with the ground truth label, we are able to compute the loss, and the loss will then be used to compute the gradients for the parameters. Okay, so no matter how many layers or how many filters we use, we can always back propagate the gradients to the parameters. Okay, and we use the gradients to update the parameters. So these gradients, so these parameters in the filters are just like the weight matrix in the regular neural network. So they will be updated. And after the learning is done, then these parameters, they can be fixed now. They can be used as some fixed filters. And these filters will be useful in the particular task that we define here. For example, if the training data is labeled with edges, then the resulting filter is capable of detecting edges. If the label is about objects, right, whether it's a hand or it's not, then the resulting filters can be used to do that prediction. Okay, so the filters, they are not predefined. It's learned from the data, and that is basically the simple idea. No, so during the first forward pass, it's not necessary to use any predefined filters. The filters can be initialized to random numbers, just like the way we initialize our regular neural network, right? We use the, remember the Xavier normal way of initializing the deep neural network, right? It's just random numbers. And that's the same thing for the future. It can be initialized to random numbers, but it will gradually pick up which will convert to the minimum points, or the theoretical minimum points during training, guided by the gradient descent algorithm. So these W's has nothing to do with the predefined filters at all. This can totally be learned from scratch. All right. So now let's go back to the arithmetic rules or principles of the mapping the sizes, because we mentioned that it's not always that given the inputs of 6 and the filter of 3, we can always get 4. Okay, so it can be we can have some different results. We can have some variations. Okay, so we use the notation n to indicate the size for the inputs and f for the filter. Okay, so this is the most common case. If the input is n, filter is f, then because there are 4 possible positions for fitting a 3x3 filter into a 6 by 6 matrix, then the resulting matrix will be determined by this formula, n minus f plus 1. Okay, that's something we already recognize, right? So the downside of this regular operation is that the output shrinks. Okay, so that means we neglect some information in the original data. Then how do we avoid this? Is that we can set something called padding. Okay, so here, before I go to the next slide, this this yellow region pixel is only used once, right? It's only used in the first computation. Then it's moved to the filter is moved to the right. Okay, but if we look at this cell, the green cell, it's first covered in this computation, right? And after this computation is done, the filter moved to the right, it's still covered. Okay, and one more step, it's still covered. So the most central elements, they are used for more times than the outside regions. So that is a loss of information because some of the pixels are just ignored. So how do we avoid this? We use some technique called padding. Okay, so it's also a straightforward technique. We just before we conduct the convolution operation, we will pad the images with some default values like 0. We can 0 pad the image, or we can use other values. But 0 is a default, it's a common choice. Okay, and we pad the image with one additional pixel on each direction. Okay, so to the left, we pad with 1 pixel, and to the right, 1 pixel. Up and down, we also pad with 1 pixel. So as a result, we make the 6 by 6 original image into an 8 by 8, and that increases the size. Okay, so as a result, now if we apply a 3 by 3 filter onto a 8 by 8 new input, it will give us a 6 by 6, because this time the n is an updated value. Okay, we use n prime to minus f plus 1. It will give us 6 by 6. Okay, and now we are satisfied because we kept the original size of the image, 6 by 6. Okay, so if you don't want to lose any information in the original image, you can choose to first zero pad the image with 1 pixel, and then apply the 3 by 3 matrix, 3 by 3 filter. Okay, alrighty. So this is something called one padding. Okay, we pad 1 additional pixel. So of course we can choose to pad with different sizes. So now again, given this 6 by 6 image, what if we pad with 2 pixels? It will give us a 10 by 10 enlarged image, right? And the results of applying the same filter will give us even larger outputs, which is 8 by 8. Okay, so we can summarize the general principle by this updated formula. Okay, it's no longer n minus f plus 1, but we consider the padding, the effects of the padding. Okay, and we use p to indicate the size of padding operations. Okay, so basically we can look at 2 types of paddings, or 2 types of convolution. Okay, so the first one, valid convolution, it means that there's no padding. All right, so that will reduce to to the original case, which will result in n minus f plus 1. And the other type is called same padding, which means we don't change the size of the inputs data. Okay, we use the padding so that the input size equals output size. Okay, so that means we use the padding P, and that is the size of the output. We want output to be equal the input size. Okay, so if we use this equation and eliminates n, which will give us that the padding should be f minus 1 over 2. Okay, so going back to the example we use, the filter is 3 by 3, right? 3 by 3 minus 1, 3 minus 1 divided by 2 is 1. Okay, so if the filter is a 3 by 3 filter and we don't want to change the input size, then we basically need to the padding of size 1. Okay, you see that given different filter size, if we want to keep the image the same size, we should use different values for padding accordingly. All right, so that's so much for padding. Okay, then it comes to the next technical points, the strided convolution. Okay, so it means, so the term stride means the step that we take each time we move the filter. Like think of filter as a window. Each time we move that window. So all the previous examples, we move the window by 1 pixel. Okay. So if now we move the filter with a stride of 2, which means we move the window 2 pixels at a time. Okay. So the inputs, the 7 by 7 inputs with the 3 by 3 filter will result in a 3 by 3 output. You see the output is very small because now each time we take a larger step. Okay, so the first element is the top left region with its dot product with the filter, and we got 5.4. So the next, and look carefully, now we move to the right by 2 pixels, not by 1, because we set the stride to be 2. Okay, so the element here is the dot product between this region with the filter. Okay, and a step of 2 pixels is defined by the stride of 2. Okay, and the next step, if we move 2 more steps to the right, and luckily we can have 1 more complete green region. Okay, and that is also due to the fact that we use a 7 by 7 inputs, and that happened to have 3 outputs, 3 complete outputs in a row. Okay, and we'll see in a later example that if we cannot move to the right with the stride step, then we will simply do not do that. Okay, so this is the, okay, so one more technical point is that when we move downwards, we also need to move 2 pixels. Okay, that is the results of the second row and the third row. Okay, so with stride 2, we will have a 3 by 3 outputs from the original 7 by 7 inputs. Okay, so let's generalize. Let's basically summarize the principles. It will be something like n plus 2p minus f. P is the padding. Okay, we still consider padding. So if stride is considered, then we need to divide it by the stride and then round it to the floor. Okay, and in the next slide, we're going to show why we need to use this round to the floor operation. Okay, so here the input is 6 and the filter is 3, and the S is 2, the strata is 2. So using the formula, 6 minus 3 divided by 2 is 1.5, and we round it to the floor, results in 1. So the result is a 2 by 2 matrices. So because if we observe, if you look at it closely, that is the first element, right? And the next move is 2 pixel to the right. Okay. The next, after this step is done, we still want to go 2 pixels to the right, but we will exceed the right boundary. Okay, and we reach at some points the outside region that we don't know the values. So in this case, we will do not do this step. Okay, and that's why we basically use the rounded to the floor operation to compute the output size. Okay. All right. So after the basics are done, now let's look at a more complex case in which the input is not a flat matrix, but also but it's a 3D volumes. Okay, because it is a more common case when we deal with color image. So you can imagine a RGB image as 3 layers of matrices. Okay, 1 layer for one color. So we call these layers channels. The R channel covers stores the pixels for the red color. The B channel is for the blue color. The G channel for the green colors. So now the inputs, it's a volume, it's a cube, it's a 6 by 6 by 3. So we call this first dimension as height. It's the number of rows. And the 6th dimension is width. It's the number of columns in a matrix. And the third quantity, in the third dimension 3, is the number of channels. Okay, so for a color image, the number of channels is usually 3. Okay, and in order to apply convolution over a volume that has 3 channels, we also need to design our filter to be a 3D filter. And it also has 3 channels. So the last dimension 3 must match the last dimension of the RGB image inputs. Okay. So the results is a 4 by 4 by 1, not by 3. Okay. It's well, we ignore the by 1 dimension here. Just make it, just think of it as a 4 by 4 matrix. Okay, because that is the rule of applying 3D volume convolutional operations. Okay, so and the details is like this. It's more or less the same thing. So we will first find the top left most cube. Okay, so within this light yellow highlighted cube, we have 3 by 3 by 3, which is 27 elements. Okay, and we use that 27 elements in the data to apply a element-wise multiplication and sum up all the products, which will result in one value. And that one value will be stored into the element here. Okay, so after this first computation is done, we will move the filter one pixel to the right, okay, which will take the second 3 by 3 by 3, which is the new 27 elements, and do the same computation with the filter, and will result in the elements within the second element. And one more step to the right until we reach the edge, okay? And of course, the padding and stride operations all apply to the convolution over 3D volumes. So maybe one special points about padding over the 3D is that when you're padding a 3D volume, you need to pad all the RGB layers, all the channels, right? When you one pad the inputs with the R channel, you should also pad the green channel and the blue channel at the same time, right? So that's the principle of convolution over 3D volumes. Next, we'll look at a more complex case in which we have more than one filters applied, okay? So having one filter will result in one 4x4 matrix in this particular example. And what if we have a second filter? Then it will give us a second 4x4 output. So if we combine these two outputs, then we will have a 4x4 by 2 cube or 4x4 by 2 volume, okay? And this quantity 2 here, we can also say this is the number of channels in the outputs, okay? But this number of channels is determined by the number of filters. Like if we use 2 filters, 1 and 2, then the results will have this by 2. What if we use one more filter? Then the results will be by 3, and so on, okay? So this number of filters has nothing to do with this number of filters, has nothing to do with this number of channels, okay? So the inputs, the channels of the inputs is not related to the number of channels in the outputs. But this number of channels needs to match the number of channels in each filter, okay? So if these 3 or these 3 doesn't match these 3, then the convolutional operation is not valid, okay? In order to have a valid convolutional operation, we must have the filter channels to match the input channels. All right, so that's the basic principle for multiple filters as shown in this formula. The n number of channels should match the number of channels here, and this number of filters will determine how many channels will be in the output volume. So of course we can apply padding and strides within this formula as well. All right. So I guess we are done today, and our goal of introducing the basics for convolutional operations is done. And in the next lecture, we're gonna look at what a convolutional layer should be in a neural network, in a convolutional neural network, and how we combine the convolutional layer with a pooling layer, and we add up all those layers together to design a simple ConvNet model, okay? And that's it for the course lecture today. And if you have questions, you can raise it now. Okay, no question. All right, good. And so we will meet again on Thursday. We'll continue our topic on convolutional neural network. See you guys. Don't forget the quiz.